Flashing across California desert skies, the airplanes you see here are writing new chapters in the story of man-made flight. There she goes.
This is my first opportunity to greet you as Deputy Administrator of the National Aeronautics and Space Administration.
Together, you and I must make our new agency
the most unusual place.
An organization that can challenge conventional wisdom.
We can engineer anything we can write the requirements for.
We're going to make your idea work. This particular idea is quite disruptive.
A typical flight, of course, starts under the wing of the B-52 mothership.
This sleek, high-speed machine would have made Rube Goldberg proud.
The manner in which we fly re-entry from space on the space shuttle was pioneered on the X-15.
The X-31 pretty much wrote the book on thrust vectoring, along with its sister program, the F-18 HAR.
An observation of an occultation is one of the more challenging missions that Sophia can do.
Right now, we are looking at the dawn of a new era of aviation.
Okay, we finish our climb check. Now it's time for a Chesterfield.
Small general-purpose planes outnumber the world's transports by 100 to 1.
And there are thousands of privately owned airplanes all over America.
The number of mistakes I've seen private pilots make over the years is astonishing.
A man must know the limits of his machine.
Engineers continually assess the technological limits of safety and aggressively seek out those advancements which offer significant promise.
The built-in dangers of flight testing showed up during this evaluation of the PA-30 Twin Comanche. The plane had a serious flutter problem, which appeared unexpectedly.
As speeds and performance of light aircraft increase, much more attention must be given to flutter and aeroelastic behavior.
The introduction of wide-body airplanes in the 70s was instrumental in satisfying the public's desire for traveling. Along with this increased mix of aircraft comes an increased concern about wake turbulence.
Wake vortex is a turbulent air condition that forms at an airplane's wingtip.
Violent whirlpools of air called vortices. One of these disturbances could last for as much as several minutes in the air, an invisible hazard.
The wake vortex from a large transport can throw a smaller plane out of control. An effort to reduce its hazards became a matter of national priority. By comparing upsets of probe aircraft flying in the wake, they proved that using selected combinations of wing flap, spoiler, and landing gear positions, they could effectively reduce the strength of the vortex.
Separation standards were developed that established aircraft weight categories and distances.
Escape technology is having a hard time keeping pace with the demands placed upon it by improved aircraft performance, more complex missions, and more low-level flying now required in the current training environment.
Today, man's life more than ever before depends on complex man-machine intercommunication. He must be aware of the soft spots.
When the Enterprise performed its approach and landing tests at Dryden, it discovered a problem in maneuvering of all fly-by-wire airplanes. It happens when the aircraft's controls don't respond to the pilot's commands as fast as he expects. The pilot automatically assumes the controls didn't get the message, so he repeats his command. Meanwhile, the computer is executing the first command, so the pilot reacts by trying to compensate for the extra command. To solve the pilot-induced oscillation problem, engineers programmed the F-8's computers to make the plane particularly susceptible to PIOs. The pilot flew the plane in the oscillation-vulnerable mode and tried a series of PIO suppression filters to find which one worked best.
It would be a fighter pilot's ultimate dream to be able to maneuver carefree at extremely high alpha.
But what happens to the total aerodynamics when we increase alpha beyond that recommended? stall, the result of an alpha so great that the air can no longer flow smoothly over the curved top surface of the wing.
Air is not moving over the control surfaces as it should, which renders the plane's controls virtually useless.
Okay, spinning 1/2 mile northeast of the spin point, Bill. That's Gary.
The F-14 is a Navy high-performance fighter. While performing certain extreme maneuvers, pilots have had problems with spin and loss of control.
Stall on the right. It's shut down. And I've got recovery.
Control modifications done here have made the F-14 easier to fly.
We were able to assist the Federal Aviation Administration in testing a new aviation fuel which was not supposed to burn if the aircraft crashed. Unfortunately, the test showed that the fuel did burn.
Two of the technologies of the second half of this century that affected major changes in aerospace are the jet engine and the digital computer.
We had no ailerons to bank the airplane. We had no rudders to turn it, no elevators to control the pitch. We had no leading edge slats for slowing the airplane down, no trailing edge flaps for landing.
NASA's Dryden Flight Research Center began to investigate ways to safely land crippled airplanes using only throttle controls.
To see what we could do with just the engines if all the flight controls were gone.
Things you do here may prevent a lot of disasters.
Central hydraulic systems tend to be very vulnerable. These power-by-wire systems aren't as vulnerable.
These experimental actuators operate independently of the F-18's hydraulic system. They could greatly reduce the costs, weight, and maintenance of future aircraft. The real-time flush air data sensing system used a group of 11 tiny pressure orifices arranged on the nose of the F-18. The system eliminates the need for external air data probes, or booms, which are sensitive to vibration and alignment errors and can be easily damaged. Another experiment will evaluate a newly developed air mass flux sensor device. The sensor may enhance safety by rapid detection of hazardous airflow conditions, which could lead to in-flight engine stalls.
Watching outside.
4, 1,
Fly up, fly up.
1, fly.
I got a flight report.
The HISTEC program evaluated a computerized system that can sense and respond to high levels of engine inlet airflow turbulence. This system could successfully prevent sudden in-flight engine compressor stalls and potential engine failures and thereby increase aircraft safety.
A clear turbulence is turbulence that give no indication of their presence. It can be very dangerous to fly through because it moves the aircraft around and damages the aircraft and the people inside. And even the most conscientious pilot has really no warning that it's present.
The garment I'm currently wearing protects me against both partial pressure and high G-force. And as you can see, the coverage is pretty extensive. In modern aircraft, heat stress becomes a very big problem. Apex is a prototype cooling garment.
The next generation in microclimate cooling.
The Intelligent Flight Control project is a project where we take a highly advanced F-15 aircraft and we add another computer to it that has a neural network in it. That neural network will actually take the errors to control surface failures and aerodynamic failures and augment those failures with self-learning neural network software. We don't tell the neural networks what actually failed. It just knows that there's an error in the system and it sends pitch, roll, and yaw commands to the flight computer and commands the aircraft properly.
If the research that we do right now results in just one saved aircraft, I think it's well worth the effort that we spent.
This research makes the aircraft more safe because what it does is it makes the aircraft more smart, able to adapt to failures. This computer would be able to take over the airplane and be able to land it safely and stabilize it.
This research has a lot of applications. Using the flight controls to help reduce the stresses on the structure. We could use it for active load alleviation or possibly active flutter or LCO suppression.
With lightweight wings, they are prone to flutter, which is a phenomenon where you go too fast and then the wing just falls apart. The X-56A project is intended by development of flight control technologies to suppress flutter, to use other control surfaces to counteract that vibration.
Since the dawn of aircraft, the ground has been an enemy of the pilot.
ACAT is the Autonomous Collision Avoidance Technology Program. Ground collision avoidance and air-to-air collision avoidance.
We decided, let's see how we can adapt this technology to other platforms. We moved the software from high-dollar fighter hardware processors to cell phone.
We'll recover! We'll recover!
From general aviation to airlines to military aviation, we can make it safer. The technology's there, we just need to put it all together and make it happen.
We're trying to correlate our radar readings with the actual readings that we're getting from in situ measurements to see if we can figure out if you can predict this high ice water content.
Right now our flight tracks are overflying the coldest temperatures that we can find, which correlates to the deepest convection going on.
Basically what the scientists are trying to do is get a baseline of how pilots breathe in tactical airplanes.
This program is going to help develop new equipment, new systems, and expand the knowledge of human physiology in order to make it safer for pilots to fly.